The Accidental Revolution: How Unintentional Discoveries Changed Our World. A journey through history's greatest accidental breakthroughs. Prologue. The beautiful chaos of discovery. Pictured this: a scientist frantically cleaning up what appears to be a contaminated experiment, cursing their carelessness, only to realize they've stumbled upon one of the most important medical discoveries in human history. Or imagine an engineer's failed adhesive becoming the foundation for a billion-dollar industry that changed how we organize our lives forever. History is filled with such moments, instances where human error, curiosity, and sheer accident converged to create breakthroughs that would reshape civilization. These aren't just feel-good stories about happy accidents. They represent a fundamental truth about innovation. Sometimes the most profound discoveries come not from meticulous planning, but from the unexpected collision of preparation and chance. What makes these stories so captivating isn't just their serendipitous nature, it's the reminder that in our quest for knowledge and progress, we must remain open to the unexpected. The greatest discoveries often hide in the shadows of our failures, waiting to be recognized by minds prepared to see opportunity where others see only mistake. As we embark on this journey through history's most fascinating accidental discoveries, prepare to be amazed by how often the path to revolutionary change began with someone saying, "That's odd, or "This wasn't supposed to happen, These moments of unplanned revelation have given us life-saving medicines, revolutionary technologies, delicious foods, and scientific principles that continue to shape our understanding of the universe. Chapter 1. The Moldy Miracle. Penicillin's accidental birth. The stage is set. The year was 1928, and the world was still reeling from the devastating effects of World War I. Infectious diseases remained one of humanity's greatest killers, claiming millions of lives annually. In hospitals across the globe, doctors watched helplessly as patients succumbed to infections that would seem trivial by today's standards. A simple cut could lead to sepsis and death. Pneumonia, tuberculosis, and other bacterial infections were death sentences for countless individuals. In this grim landscape, a Scottish bacteriologist named Alexander Fleming was working at St. Mary's Hospital in London. Fleming was studying Staphylococcus bacteria, the same microorganisms responsible for many deadly infections. His laboratory was cluttered with petri dishes containing bacterial cultures, a common sight in microbiology labs of the era, but Fleming had a reputation for being somewhat disorganized. His colleagues often remarked on the chaotic state of his workspace, with petri dishes stacked haphazardly and experiments left unattended for days. Little did anyone know that this apparent carelessness would soon lead to one of the most important medical discoveries in human history: the fateful contamination on September 3, 1928. Fleming returned to his laboratory after a 2-week vacation. As he began cleaning up his workspace, he noticed something peculiar about one of his bacterial culture plates. The dish, which should have been uniformly covered with golden yellow Staphylococcus colonies, had been contaminated by what appeared to be a blue-green mold. Any other scientist might have simply discarded the contaminated plate as a failed experiment. After all, contamination was the bane of every microbiologist's existence. But something about this particular contamination caught Fleming's trained eye. Around the mold, there was a clear zone where the bacteria had been killed or prevented from growing. This wasn't just contamination, this was something extraordinary. The mold had somehow created a bacteria-free zone around itself, suggesting that it was producing a substance with powerful antibacterial properties. Fleming's scientific instincts kicked in. Instead of throwing away the ruined experiment, he began to investigate this mysterious mold more closely. The investigation deepens. Fleming's first task was to identify the mold that had contaminated his bacterial culture. Through careful examination and testing, he determined that it belonged to the genus Penicillium, the same family of molds commonly found on bread and other organic materials. This seemingly ordinary household mold was producing something that could kill dangerous bacteria. The discovery process wasn't immediate or dramatic. Fleming spent weeks carefully cultivating the mold and testing its effects on various bacterial strains. He found that the substance produced by the mold, which he named penicillin after the Penicillium genus, was effective against a wide range of harmful bacteria, including Streptococcus, Pneumococcus, and gonorrhea. Even more remarkably, Fleming discovered that penicillin appeared to be non-toxic to human cells. This was crucial because many substances that could kill bacteria were also harmful to human tissue. Penicillin seemed to selectively target bacterial cells while leaving human cells unharmed, a property that would make it an ideal medicine. The struggle for recognition. Despite the obvious potential of his discovery, Fleming faced significant challenges in developing penicillin into a practical medicine. The substance was difficult to purify and stabilize, and Fleming lacked the resources and expertise needed to mass-produce it. His initial attempts to interest pharmaceutical companies and fellow researchers met with lukewarm responses. Fleming published his findings in 1929, but the scientific community largely overlooked the paper. The discovery of penicillin might have remained a curious footnote in medical history, if not for the outbreak of World War II, and the urgent need for new ways to treat infected wounds. The Oxford team steps in 1939. A team of researchers at Oxford University, led by Howard Florey and Ernst Boris Chain, rediscovered Fleming's work. They recognized the enormous potential of penicillin and set about developing methods to purify and mass-produce the drug. Their efforts were motivated by the pressing need to treat battlefield injuries and infections that were claiming thousands of lives. The Oxford team's work was fraught with challenges. They had to develop entirely new methods for cultivating the mold, extracting the active compound, and purifying it to pharmaceutical standards. Their first batch of penicillin was produced in improvised equipment, including bedpans and milk churns pressed into service as fermentation vessels. The first human test of penicillin occurred in February 1941. Police Constable Albert Alexander had scratched his eye on a rose thorn, leading to a severe infection that was spreading throughout his face and body. Traditional treatments had failed, and Alexander was dying. The Oxford team administered their precious supply of penicillin to Alexander, and the results were dramatic. The infection began to clear, and Alexander showed signs of recovery. However, the team's supply of penicillin ran out before the treatment could be completed. Without the antibiotic, the infection returned with a vengeance, and Alexander died a month later. This tragic outcome highlighted both the incredible potential of penicillin and the urgent need to develop methods for mass production. The team refined their approach and conducted more trials, this time ensuring they had sufficient quantities of the drug to complete the treatment courses. Mass production and global impact. By 1942, the benefits of penicillin were undeniable, and pharmaceutical companies on both sides of the Atlantic began working to mass-produce the drug. The development of deep-tank fermentation methods allowed for the production of penicillin on an industrial scale. The impact was immediate and profound. During World War II, penicillin saved countless lives that would have been lost to infected wounds and battlefield injuries. After the war, the antibiotic revolution transformed medicine, making routine surgeries safer and turning previously fatal infections into manageable conditions. Fleming's accidental discovery had grown into a medical revolution that would save hundreds of millions of lives over the following decades. The story of penicillin remains one of the most compelling examples of how scientific breakthroughs can emerge from the most unexpected circumstances. The deeper mystery, but here's where the story becomes even more intriguing. How did the penicillium mold end up in Fleming's laboratory in the first place? For decades, this remained a mystery that added an element of cosmic coincidence to an already remarkable tale. Recent investigations have revealed that the contamination likely came from a mycology laboratory located one floor below Fleming's workspace. The spores had somehow traveled upward, possibly through air currents or on someone's clothing, and settled into Fleming's bacterial culture at precisely the right moment to create the conditions for discovery. The timing was crucial. If Fleming had returned from vacation a day earlier or later, if the temperature had been different, if he had been more meticulous about cleaning up his cultures, any of these factors could have prevented the discovery. The convergence of multiple accidents and oversights created the perfect storm for one of medicine's greatest breakthroughs. The ripple effects. Fleming's accidental discovery didn't just give us penicillin, it launched the entire antibiotic era. The success of penicillin inspired researchers to search for other naturally occurring antimicrobial compounds, leading to the discovery of streptomycin, tetracycline, and dozens of other life-saving antibiotics. The pharmaceutical industry was transformed as companies invested heavily in antibiotic research and development. New techniques for screening microbial compounds were developed, and the systematic search for antibiotics became a major scientific endeavor. Perhaps most importantly, Fleming's discovery changed how we think about medical research. It demonstrated that breakthrough discoveries could come from unexpected sources, and that maintaining an open mind about failed experiments could lead to revolutionary insights. Chapter 2. The Sweet Mistake, Artificial Sweeteners, and Accidental. Taste the quest for sugar alternatives. The story of artificial sweeteners begins not with a search for sugar substitutes, but with entirely different scientific pursuits that led to surprisingly sweet discoveries. These accidental breakthroughs would revolutionize the food industry and provide alternatives for millions of people with diabetes and other health conditions. Saccharin. The first sweet accident, 1879, Konstantin Fahlberg, a chemist working at Johns Hopkins University, was investigating coal tar derivatives, a common area of research in the late 19th century when coal was a major industrial resource. Fahlberg was specifically studying the oxidation of otolinous velphenol, a compound with no known connection to sweetness or food. The discovery happened in the most mundane way possible. After a long day in the laboratory, Thalberg went home for dinner without thoroughly washing his hands, a common oversight that would be unthinkable in today's safety-conscious laboratories. As he began eating his meal, he noticed that his bread tasted remarkably sweet. At first, he thought his wife had added sugar to the recipe, but she assured him that nothing had been changed. Thalberg realized that the sweetness must be coming from something on his hands. The next day, he returned to his laboratory and began systematically tasting various compounds he had been working with. An incredibly dangerous practice that would horrify modern chemists. When he tasted the otolinous sulfonamide he had been synthesizing, he discovered the source of the sweetness. The compound that would become known as saccharin was hundreds of times sweeter than sugar, but it had a distinctly bitter aftertaste that made it less than ideal as a sugar substitute. Despite this limitation, Thalberg recognized the commercial potential of his discovery and patented the compound in 1884. The controversy and acceptance saccharin's journey from laboratory curiosity to commercial product was fraught with controversy. Early critics questioned the safety of consuming a coal tar derivative, and the bitter aftertaste limited its acceptance among consumers. However, sugar shortages during World War I created a market for saccharin, and it began to gain acceptance as a sugar substitute. The artificial sweetener faced periodic challenges from health authorities and sugar industry interests, but it survived numerous safety investigations and regulatory reviews. Today, saccharin remains one of the most widely used artificial sweeteners in the world, found in diet sodas, sugar-free gum, and countless other products. Cyclamate, the graduate student's discovery. The next major artificial sweetener discovery came from another unexpected source. In 1937, Michael Spada, a graduate student at the University of Illinois, was working on his doctoral thesis involving the synthesis of anti-fever drugs. His research focused on sulfamic acid and its derivatives, compounds that had potential therapeutic applications. During one of his experiments, Spada was working with cyclohexylsulfamic acid when he decided to take a cigarette break, a common practice in laboratories of the era. Without thinking, he placed his cigarette on the laboratory bench where it came into contact with some of the compound he had been synthesizing. When Spada returned to his work and picked up his cigarette, he noticed an intensely sweet taste. Like Thalberg before him, he traced the sweetness back to the compound he had been working with. Cyclohexylsulfamic acid, later known as cyclamate, was even sweeter than saccharin and had a much cleaner taste profile. Spada's advisor initially dismissed the discovery as unimportant, focusing instead on the intended pharmaceutical applications of their research. However, Spada recognized the potential of his accidental discovery and eventually developed cyclamate into a commercial sweetener. Aspartame, the ulcer drug that became a sweetener, perhaps the most famous accidental sweetener. Discovery occurred in 1965 at the laboratories of G.D. Searle and Company. James Schlatter, a chemist working on developing new treatments for gastric ulcers, was synthesizing aspartylphenylalanine methyl ester as part of his research into gastrin, a hormone involved in digestion. The discovery happened during a routine synthesis procedure. Schlatter was heating a mixture of aspartic acid and phenylalanine methyl ester when some of the compound splashed onto his fingers. Later, when he licked his finger to pick up a piece of paper, he noticed an intense sweet taste. Intrigued by this unexpected property, Schlatter began investigating the sweetening potential of his compound. He found that aspartylphenylalanine methyl ester, later named aspartame, was approximately 200 times sweeter than sugar and had a taste profile much closer to natural sugar than previous artificial sweeteners. The long road to a path to commercial success was longer and more complex than that of previous artificial sweeteners. The compound's approval process was complicated by safety concerns and regulatory challenges that took nearly 2 decades to resolve. The primary concern centered on aspartame's metabolism in the human body. When consumed, aspartame breaks down into 3 components: aspartic acid, phenylalanine, and methanol. While these components are naturally occurring and generally safe, the presence of phenylalanine raised concerns for individuals with phenylketonuria, a rare genetic disorder that prevents the proper metabolism of this amino acid. After extensive testing and regulatory review, aspartame was finally approved for use in dry foods in 1981 and for carbonated beverages in 1983. The approval opened the floodgates for diet sodas and sugar-free products, revolutionizing the food industry and providing options for diabetics and weight-conscious consumers. Sucralose, the misunderstood instruction net. Discovery of sucralose in 1976 involved what might be the most amusing miscommunication in the history of artificial sweeteners. Shashi Kant Fadnis, a graduate student at King's College London, was working with Professor Leslie Hawke on developing new insecticides based on chlorinated sugars. During one of their experiments, Professor Hawke instructed Fadnis to test a chlorinated sucrose compound they had synthesized. However, due to Fadnis's limited English proficiency, he misunderstood the instruction as taste rather than test, following what he thought were his professor's directions. Fadnese tasted the compound and discovered its intense sweetness. The compound, later named sucralose, was approximately 600 times sweeter than sugar and had an excellent taste profile with no bitter aftertaste. Unlike previous artificial sweeteners, sucralose retained its sweetness even when heated, making it suitable for cooking and baking applications. The science behind the sweetness. What makes these accidental discoveries so remarkable is that they all involve compounds that were never intended to interact with human taste receptors. The sweetness of these artificial compounds results from their molecular structure, coincidentally matching the binding sites on our taste buds that detect sweetness. Human sweetness perception is mediated by a protein complex called the T1R2, T1R3 receptor, which binds to sweet-tasting molecules and triggers the sensation of sweetness. Natural sugars have evolved to activate these receptors as part of our biological drive to seek out energy-rich foods. The artificial sweeteners discovered through these accidents happen to have molecular shapes that also activate these same receptors, despite being chemically unrelated to natural sugars. This molecular mimicry is extraordinarily unlikely to occur by chance, which makes these accidental discoveries all the more remarkable. The fact that multiple unrelated compounds, discovered through completely different research programs, all happen to activate our sweetness receptors suggests that the binding sites for these receptors are more flexible than initially understood. The industry impact. The accidental discovery of artificial sweeteners created an entirely new segment of the food industry. Diet sodas, sugar-free candies, and low-calorie desserts became billion-dollar markets, driven by consumers' desire to reduce their sugar intake while maintaining the sweet taste they craved. These discoveries also had profound implications for public health. Artificial sweeteners provided options for diabetics who needed to limit their sugar consumption, and they offered tools for weight management in an era of increasing obesity rates. The availability of sweet-tasting, low-calorie alternatives helped many people reduce their overall caloric intake without sacrificing the pleasure of sweet foods. The ongoing sweet revolution, the accidental discovery of artificial sweeteners, opened the door to more systematic research into sweet-tasting compounds. Scientists began deliberately searching for new sweeteners, leading to the development of compounds like stevia extracts, monk fruit sweeteners, and other natural and artificial alternatives. Each of these original accidental discoveries teaches us something profound about the nature of scientific research. They remind us that breakthrough discoveries can come from the most unexpected sources, and that maintaining an open mind about unusual observations can lead to revolutionary insights. The sweet accidents that gave us artificial sweeteners also highlight the importance of curiosity and careful observation in scientific research. In each case, the scientists could have dismissed the sweet taste as irrelevant to their research goals. Instead, they chose to investigate these unexpected observations, leading to discoveries that would benefit millions of people worldwide. Chapter 3. The Microwave Revolution. From radar to reheated dinners, the birth of radar technology. To understand how the microwave oven came to be, we must first journey back to the early days of World War II, when radar technology was being rapidly developed to detect enemy aircraft and ships. The story begins with a technology that would prove crucial to the war effort, but its domestic applications were entirely unforeseen. Radar systems work by emitting high-frequency electromagnetic waves and detecting their reflections off distant objects. During the war, these systems used a revolutionary new device called the magnetron, a vacuum tube capable of generating extremely powerful microwave radiation. The magnetron was a closely guarded military secret, representing a significant technological advantage for the Allied forces. Percy Spencer, the inventor who walked into history. Percy Spencer was a self-taught engineer working for Raytheon, a company heavily involved in manufacturing radar equipment for the military. Born into poverty in rural Maine, Spencer had little formal education but possessed an extraordinary intuitive understanding of electronics and electromagnetic phenomena. His colleagues often marveled at his ability to troubleshoot complex radar systems and improve their performance. Spencer's background made him uniquely positioned to make the discovery that would change kitchens around the world. His hands-on approach to engineering and his willingness to work closely with dangerous, high-powered equipment put him in direct contact with the microwave radiation that most other engineers experienced only indirectly. The chocolate bar that changed everything. The pivotal moment occurred in 1945, during one of Spencer's routine inspections of a military radar installation. He was standing in front of an active magnetron, the device that generated the powerful microwaves used by the radar system. In his pocket, he carried a chocolate bar, a simple snack that would soon become one of the most famous confections in the history of technology. That as Spencer worked near the magnetron, he noticed something peculiar happening in his pocket. The chocolate bar was melting, not from ambient heat, but from something else entirely. The chocolate was becoming soft and gooey, despite the fact that the room was not particularly warm. This observation puzzled Spencer, who had spent years working with radar equipment without noticing such an effect. A less curious individual might have attributed the melting chocolate to body heat or room temperature. But Spencer's engineering mind immediately recognized that something unusual was occurring. He understood that the timing of the chocolate's melting, coinciding with his proximity to the active magnetron, was too precise to be coincidental. The popcorn experiment. Spencer's scientific instincts kicked in immediately. Rather than dismissing the incident as a curious anomaly, he decided to investigate further. The next day, he brought popcorn kernels to the laboratory, a choice that would provide dramatic, visual evidence of microwaves' heating properties. When Spencer placed the popcorn kernels near the active magnetron, the results were spectacular. The kernels began popping rapidly, much faster than they would in a conventional heating method. The microwaves were causing the moisture inside the kernels to heat up rapidly, creating steam pressure that caused them to explode into fluffy popcorn. This experiment demonstrated that microwaves could heat food from the inside out, a fundamentally different mechanism from conventional cooking methods that rely on heating the surface of food and allowing that heat to gradually penetrate inward. Spencer realized he had stumbled upon an entirely new method of cooking. The egg experiment and its messy consequences encouraged by the popcorn results. Spencer decided to try a more complex experiment. He placed a raw egg near the magnetron to see how microwaves would affect it. This experiment would provide both insight into the heating mechanism and a memorable demonstration of microwave cooking's power. The results were both enlightening and messy. The egg began heating rapidly from the inside, causing it to explode dramatically and covering Spencer and nearby equipment with cooked egg. While the cleanup was unpleasant, the experiment provided crucial information about how microwaves interact with foods containing water. Spencer realized that microwaves specifically targeted water molecules, causing them to vibrate rapidly and generate heat through friction. This explained why foods with high water content heated so quickly, and why the heating occurred throughout the food rather than just on the surface. From military secret to kitchen appliance, Spencer's discovery presented both an opportunity and a challenge. The magnetron technology was still classified as a military secret, and the idea of using it for cooking food seemed almost absurd to many of his colleagues. However, Spencer was convinced that he had discovered something revolutionary. Working with his team at Raytheon, Spencer began developing a practical cooking device based on microwave technology. The first challenge was creating a contained environment where microwaves could safely heat food without exposing users to dangerous radiation levels. They developed a metal enclosure that would contain the microwaves while allowing users to place food inside for heating. The Raytheon, the first microwave oven. In 1947, Raytheon introduced the first commercial microwave oven, called the Raytheon. The device was enormous, standing nearly 6 feet tall and weighing over 750 pounds. It cost $5,000, equivalent to about $60,000 in today's currency, making it affordable only for restaurants and industrial food service operations. The early Raytheon was water-cooled and required its own electrical system due to its enormous power requirements. Despite these limitations, it represented a revolutionary leap in cooking technology. Foods that traditionally took hours to cook could be prepared in minutes, and the heating was more uniform than conventional methods. The slow path to consumer acceptance. The journey from Spencer's accidental discovery to widespread consumer adoption took decades. Early microwave ovens faced significant skepticism from both consumers and food safety regulators. Many people feared that microwaved food might be radioactive or somehow harmful, despite scientific evidence to the contrary. The size and cost of early microwave ovens limited their market to commercial applications. Restaurants and airlines began using them to quickly reheat pre-prepared meals, but home use remained rare. The technology needed significant miniaturization and cost reduction before it could enter residential kitchens. Technological improvements and market expansion. Throughout the 1960s and 1970s, engineers worked to make microwave ovens smaller, safer, and more affordable. The development of more efficient magnetrons reduced power requirements, while improved shielding made the ovens safer for home use. Manufacturing improvements gradually brought costs down to levels that middle-class families could afford. The introduction of countertop models in the early 1970s marked a turning point in consumer acceptance. These smaller, more affordable units could fit into existing kitchens without requiring special installation or electrical modifications. As prices continued to fall and convenience became increasingly valued by busy families, microwave adoption accelerated rapidly. The cultural impact of microwave cooking. The microwave oven didn't just change how we cook. It fundamentally altered our relationship with food and time. The ability to quickly reheat leftovers extended the practical life of prepared foods and made meal planning more flexible. Frozen dinners and other convenience foods were redesigned specifically for microwave preparation. The speed and convenience of microwave cooking supported changing lifestyles. As more families had two working parents and less time for traditional food preparation, the microwave oven became a symbol of modern life's accelerated pace and the prioritization of convenience over traditional cooking methods. The science behind the heating Spencer's accidental discovery revealed fundamental principles about how electromagnetic radiation interacts with matter. Microwaves operate at a frequency of 2.45 GHz, which corresponds to the resonant frequency of water molecules. When exposed to this frequency, water molecules begin rotating rapidly, generating heat through molecular friction. This heating mechanism explains why foods with high water content heat more quickly in microwaves, and why the heating occurs throughout the food volume rather than from the surface inward. It also explains why certain materials, like glass and most plastics, remain cool in microwaves. They don't contain water molecules that can absorb the microwave energy. Unintended consequences and new discoveries. Spencer's accidental discovery led to numerous other applications of microwave technology beyond cooking. Medical diathermy treatments use controlled microwave radiation to heat tissue for therapeutic purposes. Industrial applications include drying materials, curing adhesives, and processing foods on a large scale. The development of microwave ovens also contributed to advances in electromagnetic shielding and safety standards. The need to contain microwave radiation safely led to improved understanding of electromagnetic field interactions and better protective technologies. The ripple effects of accidental innovations. Spencer's chocolate bar melting in his pocket illustrates how accidental discoveries can have far-reaching consequences that extend well beyond their original context. His observation of an unexpected phenomenon led not only to a new cooking technology but to entire industries built around convenience foods, changes in family dining patterns, and advances in electromagnetic engineering. The story also demonstrates the importance of curiosity and systematic investigation when unexpected phenomena occur. Spencer could have simply attributed his melted chocolate to environmental factors and moved on with his work. Instead, his decision to investigate the anomaly led to one of the most significant innovations in food preparation technology. Today, billions of microwave ovens operate around the world, all tracing their lineage back to that moment when Percy Spencer noticed his chocolate bar melting near a radar magnetron. The accidental discovery that began with a simple snack in an engineer's pocket grew into a technology that fundamentally changed how we think about food preparation and domestic convenience. Chapter 4. The Post-it Note Phenomenon. From failed adhesive to office essential, the search for superglue. The story of Post-it notes begins with a scientist trying to create the exact opposite of what he ultimately discovered. In 1968, Dr. Spencer Silver was working in the laboratories of 3 Meters Company in Minnesota, tasked with developing new adhesive technologies. The goal was ambitious: create an adhesive stronger than anything currently available, superglue that could revolutionize industrial bonding applications. 3M had built its reputation on adhesive technologies. From Scotch tape to industrial bonding agents, the company's researchers were constantly pushing the boundaries of what adhesives could do, seeking stronger, more durable, and more versatile bonding solutions. Silver's project was part of this ongoing effort to maintain 3M's leadership in the adhesive industry. Silver was experimenting with acrylate polymers, complex molecules that could potentially form incredibly strong bonds between surfaces. His laboratory was filled with sophisticated equipment for measuring adhesive strength, durability, and performance under various environmental conditions. Everything about his research was designed to maximize bonding power. The failure that wasn't after months of careful experimentation. Silver synthesized a new adhesive compound that seemed to violate everything he knew about effective bonding agents. Instead of creating an incredibly strong permanent bond, his new adhesive was weak, temporary, and easily removable. Worse still, it could be repositioned multiple times without losing its adhesive properties. By conventional standards, Silver's new adhesive was a complete failure. It couldn't hold heavy objects, it didn't create permanent bonds, and it seemed to have no practical applications in 3M's existing product lines. Any other researcher might have discarded the compound and moved on to more promising formulations, but Silver was intrigued by the unique properties of his failed adhesive. The compound created what he described as a low-tack, pressure-sensitive adhesive that could stick to surfaces without damaging them upon removal. It was repositionable, reusable, and left no residue properties that seemed useless for industrial applications but might have value in other contexts. The sphere-shaped microscopic structures. What made Silver's adhesive so unusual was its microscopic structure. Instead of forming a continuous film like conventional adhesives, Silver's compound created tiny spherical particles that provided adhesion through van der Waals forces rather than chemical bonding. These microscopic spheres could make contact with surfaces without penetrating or chemically bonding to them. This unique structure explained the adhesive's unusual properties. The spherical particles could stick to surfaces with enough force to hold lightweight objects, but they could also be easily removed without damaging the surface or losing their adhesive properties. The adhesive could be repositioned multiple times because the spherical particles simply made new contact points with surfaces. Silver recognized that he had created something entirely new in the world of adhesives, but he struggled to find practical applications for his discovery. He spent years trying to interest various 3M divisions in his repositionable adhesive, but none could see commercial potential in a weak adhesive that couldn't create permanent bonds. Art Fry and the Singing Revelation. Breakthrough came from an unexpected source, a church choir. Art Fry, another 3-meter scientist and amateur inventor, sang in his church choir and was frustrated by bookmarks that constantly fell out of his hymnal. Traditional bookmarks were either too permanent, damaging the pages, or too temporary, falling out at crucial moments during services. Fry attended one of Silver's internal presentations about his repositionable adhesive and immediately recognized its potential for his bookmark problem. He envisioned small pieces of paper coated with Silver's adhesive that could mark pages temporarily without damaging them. These bookmarks could be easily repositioned and reused multiple times. The bootleg development project, inspired by the possibility of solving his bookmark problem, Fry began experimenting with Silver's adhesive in his spare time, using 3M's 15% time policy, which allowed employees to spend 15% of their work time on personal projects. Fry began developing what would eventually become Post-it notes. The development process was more challenging than Fry initially anticipated. Creating a paper substrate that would work with Silver's adhesive required extensive experimentation with different paper types, coating techniques, and adhesive concentrations. The adhesive had to be strong enough to hold the paper in place, but weak enough to be easily removed without damaging surfaces. Fry also had to solve the manufacturing challenges of applying Silver's adhesive to paper consistently and economically. Traditional adhesive application methods didn't work well with a repositionable compound, requiring the development of entirely new coating processes. The internal resistance, despite Fry's enthusiasm and early prototypes, Post-it notes faced significant internal resistance. At 3M, market research indicated that consumers didn't see the need for repositionable notes, and the product didn't fit into any of 3M's existing product categories. The manufacturing costs were higher than traditional adhesive products, and the market demand was uncertain. Many 3M executives questioned whether there was actually a market for repositionable notes. After all, people had been using paper and tape for centuries without expressing dissatisfaction with permanent adhesive solutions. The concept of a temporary adhesive product seemed to contradict fundamental principles of what adhesives were supposed to do. The product development team faced budget constraints and skepticism from multiple levels of management. Several times, the Post-it note project was nearly canceled due to lack of clear market demand and uncertain profitability projections. The Boise Test Market in 1977, 3M decided to conduct a limited test market for Post-it notes in Boise, Idaho. The results were initially disappointing. Consumers didn't understand the product concept, and sales were far below expectations. The test seemed to confirm the skeptics' predictions that there was no significant market for repositionable notes. However, the test market revealed an important insight. While people didn't initially understand the value of Post-it notes, those who tried them became enthusiastic users. The challenge wasn't creating a better product, it was helping people understand how the product could be useful in their daily lives. This observation led to a revised marketing strategy focused on sampling and demonstration, rather than traditional advertising. Instead of trying to explain the benefits of Post-it notes, 3M decided to give away free samples and let people discover the benefits through direct experience. The secretary strategy. The breakthrough marketing strategy emerged from observing how Post-it notes were actually being used, rather than serving primarily as bookmarks. Fry's original application. People were using them for temporary messages, reminders, and annotations. Secretaries and office workers were particularly enthusiastic users, finding countless applications for repositionable notes in their daily work. 3M developed a targeted sampling program focused on secretaries and administrative assistants in major corporations. Representatives would visit offices and distribute free samples of Post-it notes, demonstrating various uses and encouraging experimentation. This grassroots approach proved far more effective than traditional advertising methods. The secretary strategy worked because it targeted the people who would actually use the product most frequently, and who had the influence to recommend office supply purchases. As secretaries became enthusiastic Post-it note users, they began requesting the product for their offices, creating genuine market demand. The viral adoption. Once people began using Post-it notes regularly, adoption spread rapidly through organizations and social networks. The product's unique properties made it inherently viral. People would see others using colorful repositionable notes and want to try them themselves. The visual nature of Post-it notes made them natural conversation starters and demonstration tools.